Material from asteroid Bennu holds surprises. In samples taken from the Bennu asteroid, scientists found large amounts of magnesium, sodium and phosphorus, which surprised the team analyzing the material because these elements are rarely seen in meteorites. Previous analyses indicated high carbon and water content in the samples delivered to Earth. At the end of September, the OSIRIS-REx spacecraft delivered a capsule containing valuable samples of material from the asteroid Bennu to Earth. Initial tests indicated high carbon and water content in the samples. Researchers also noticed the presence of clay minerals. In the new analyses, scientists also found large amounts of magnesium, sodium and phosphorus. We certainly have hydrated, organic-rich remnants from the early solar system, which is exactly what we were hoping for when we planned this mission almost 20 years ago, said Dante Lauretta, principal investigator of the OSIRIS-REx mission from the University of Arizona. The scientist added that the asteroid fragments recovered so far come from the outer part of the sample container, because the interior has not yet been reached. The material delivered to Earth is dark in color and consists of small pieces up to about a centimeter in size. These pieces have a rough, cauliflower-like consistency, and stick to anything we touch them with, Lauretta emphasized. The asteroid Bennu is believed to be over 4 billion years old, meaning it dates back to when our solar system was just forming. Analysis of the collected material can tell us something more about the conditions that prevailed during the formation of our planetary system. In late 2020, NASA's OSIRIS-REx spacecraft collected fragments of the asteroid Bennu. The probe was planned to only touch the surface of the space rock. The entire maneuver was supposed to take 6 seconds. But due to the structure of the asteroid, which turned out to consist of weakly bonded rock fragments and contain many empty spaces, the maneuver took 17 seconds. The probe dived half a meter into the asteroid's surface and extracted so much material that it began to escape from the container. As a result, many more samples were collected than intended. The goal was to collect at least 60 grams of material, but there is much more. How much exactly? This is not known yet. Probably the length of the maneuver and too much collected material caused later problems on Earth. It's about opening the sample container, because it hasn't happened yet. After many attempts to open the capsule, it turned out that 2 of the 35 elements securing the head of the TAGSAM, touch-and-go sample acquisition mechanism, where the asteroid material is located, were blocked. They cannot be removed using current cleanroom-approved tools. The material analyzes so far focus on those fragments that were not sucked inside the container and stuck on its external part, inside the TAGSAM cover. According to Lauretta, the mechanism was blocked by one larger piece with a diameter of 3.5 centimeters. It makes it impossible to remove the cover to access and catalog most of the collected material. OSIRIS-REx scientists have appropriate procedures in place for handling these types of samples. It is extremely important not to contaminate the samples with terrestrial material. All tools used by the engineering team must be sterile and fit into a glove box with a constant flow of nitrogen. However, those approved for use did not fulfill their role. Currently, Engineers are developing and implementing new methods of material extraction. While waiting for new tools to be approved, they use tweezers to pick out small stones through a partially open flap. Some of this material was sent for spectral analysis at the NASA-supported Reflectance Experiment Laboratory, RELAB, in Rhode Island. Preliminary findings using spectroscopy, a scientific technique that reveals a material's composition by examining the way it reflects different wavelengths of light, show a dominant blue spectral signature. This hue is currently unexplained, but it may mean that the space rocks contain even more water than scientists initially predicted. What surprised scientists were the tiny pieces that appeared to have a bright, reflective coating. Pulling apart this brittle layer easily revealed the darker material underneath. Chemical analysis of this outer layer showed that it contained magnesium, sodium and phosphates, which Loretta says is quite strange because these elements are rarely seen in meteorites. "I've been looking at meteorites for a long time and I've never come across anything like this," Loretta said. Other pieces of Bennu contain hydrated clay minerals known as phyllosilicates, as well as carbonates, magnetite and sulfide minerals. The Bennu sample also contains organic compounds, containing carbon-carbon or carbon-hydrogen bonds, including a large number of molecules known as polycyclic aromatic hydrocarbons. Organic materials of this type have previously been discovered in meteorites on Earth. A white dwarf has been discovered in the crystallization phase. It will turn into a space diamond. As the star runs out of fuel and nuclear reactions cease, the object cools and gradually hardens. And just such an object was noticed by astronomers, in our cosmic backyard, only 104 light-years away. The temperature and mass of this white dwarf suggest that it has entered the crystallization stage that will transform the star into a huge cosmic diamond. Most stars entering the final chapter of their lives tend to shrink, become smaller, and slowly change color. Astronomers call these dense objects white dwarfs. These are the remains of small and medium-sized stars similar to our Sun. As they use up all their fuel in the core and shed their outer layers, the core that remains hot will begin to cool. This process can take billions of years. These extremely dense remnants of the star still emit thermal radiation, and are therefore visible to astronomers. It is estimated that up to 97% of the stars in the Milky Way will eventually turn into white dwarfs, including our Sun. However, the most massive stars will end their lives as neutron stars or black holes. Once the cooling process brings the remnant of the star to a certain temperature, the originally hot liquid material inside the star's core will begin to crystallize and eventually become a hard solid. Scientists compared this process to liquid water turning into ice. However, the solidification temperature of the core in white dwarfs is extremely high and is about 10 million degrees Celsius. The process of solidification, or crystallization, of material inside white dwarfs was predicted 50 years ago. But only the Gaia spacecraft's capabilities allowed astronomers to observe enough of these objects in such detail to see a pattern revealing the entire process. Now astronomers have spotted a white dwarf, which is part of a quadruple system. It is relatively close in terms of cosmic distances, only 104 light-years from Earth. Scientists indicate that the profile of the dying star, its temperature and mass indicate that it has entered the stage of crystallization. The description and results of the research have been accepted for publication in the monthly notices of the Royal Astronomical Society and are currently available in the archive preprint database. The discovery of a cooling white dwarf is not unusual. It is simply the remnant of a star that has burned up most of its fuel and then collapsed. However, as researchers found, this object is gradually crystallizing. In our work, we report the discovery of a new Sirius-like quadruple system at a distance of 104 light-years. Consisting of a crystallizing white dwarf and 3 other stars, wrote scientists led by Alexander Bennu of the University of Southern Queensland in Australia. When the fuel runs out, the star's outer material is ejected into surrounding space and the remaining core collapses into an ultra-dense object, about the size of the Earth, or the Moon, but with much more mass. Then the crystallization process begins. In the case of stars whose core consisted mainly of metallic oxygen and carbon, the atoms of these elements inside the white dwarf stop moving freely and form bonds, arranging themselves in a crystal lattice. During this process, energy is released and dissipated as heat. But we should not hope that we or our distant descendants will see it. This process is incredibly slow and will take billions of years. But will the object actually turn into a diamond? Scientists are not entirely sure whether the crystals formed in the white dwarf can be called a diamond. The density of white dwarfs is over 1 million kilograms per cubic meter, while the density of a diamond is only about 3,500 kilograms per cubic meter. Caring fathers in the world of amphibians. We are used to thinking that in the animal kingdom, juveniles are cared for by mothers, pairs of parents, or sometimes the entire herd, often supported by older siblings, and the role of the male is limited to transferring genetic material and maintaining the territory where the females reside. Meanwhile, the father's participation in the care of the offspring can be very large, and in nature the role of the male is often crucial in the process of rearing the young. When we talk about fathers' care for their offspring, many people will associate them with seahorses, i.e. sea fish from the Cygnotheridae family, in which males incubate their eggs in a special bag. Regardless of the systematic group, parental care, both provided by the father and the mother, has one goal: to increase the survival of the offspring, of course at the expense of the parents. Among modern amphibians, it is estimated that various forms of parental care occur in approximately 5%. Described species, i.e., in over 400 species, from at least 31 families and different orders found on different continents. This means that the parental care strategy has developed many times and independently in the course of evolution. 5% is relatively little. But it should be taken into account that our knowledge of the ecology of many exotic species is poor, so the share of this type of behavior is undoubtedly significantly underestimated. Interestingly, amphibians are dominated by the single-parent model, and joint care between male and female is a real rarity. In tailed amphibians, e.g. lumbless salamanders, the female mainly takes care of the offspring, while in over 2/3 of tailless amphibians, it is the fathers who are the main caregivers. Fathers' participation in the care of their offspring may last from several to several dozen days. Most often, care involves the transport of eggs, tadpoles, including ensuring proper incubation conditions. A popular example of care can be observed in the fabulously colorful tree frogs, Dendrobatidae, small amphibians popular in terrariums, zoos and nature films, in which transporting and caring for tadpoles is a very common behavior. It varies between species, and both males and females provide care. Fathers often remain near the places where the tadpoles develop until they metamorphose. However, this type of behavior is not limited to exotic tropics. Equally interesting behavior can be observed in the eZ6Zg nars, which occurs in the southeast of Europe. In this species, after fertilizing the eggs laid in ropes, the male wraps them around his hind legs and then carries them on land until the tadpoles hatch, which takes about 30 days. After about 20 days of incubating its eggs on land, the male Darwin's frog, Rhinoderma darwinii, a critically endangered species from Chile, swallows the developed larvae, which end up in an exceptionally well-developed vocal sac. During this period, tadpoles feed on secretions produced by the skin. This is an unusual example of pathotrophy in the animal world. Development in this specific incubator lasts about 6 weeks, i.e. until metamorphosis, when young centimeter-sized frogs leave their father's body. Another unusual example is the protection of larvae and young observed in the African bullfrog Pyxocephalus adspersus. Males guard the tadpoles developing in small depressions, the so-called ponds, protecting them from predators and from drying out. When there is a lack of water in the pond, the keeper can dig an appropriate channel to make up for the lack of water, or to unblock the channel through which the tadpoles can get to a new, safe place. To sum up, parental care in anuran amphibians occurs mainly in species that breed on land, where the conditions are variable and there is a high risk of non-survival of young individuals developing without care. In such an environment, parents, often fathers themselves, invest a lot of effort and raise a small number of offspring, but thanks to their efforts, mortality is low. And this strategy allows them to survive for hundreds of generations.